Based on Kepler's and Galileo's discoveries, Newton was able to conceive a law of gravitation that explained the fundamental forces behind orbital motion. The year was 1665. The month was August, and England was besieged by bubonic plague. Isaac Newton, then a 23-year-old Cambridge University student, retired to the solitude of his family farm in Lincolnshire until the plague subsided and the university reopened. Not given to inactivity, Newton composed 22 questions for himself, ranging from geometric construction to Galileo's new mechanics to Kepler's planetary laws. During the next 18 months, he immersed himself in the search for answers, and along the way developed calculus, the laws of motion, and the universal law of gravity. There's a myth that he was inspired by the fall of an apple to consider whether gravity was responsible for the motion of the moon as well. Newton never wrote about that day, but did reminisce about it to friends some 50 years later. Maybe it was just an analogy. The story of the falling apple reduces one of the greatest discoveries to a simple idea. Newton had been struggling to find an explanation for the basic rules of planetary motion, which had been laid down by Johannes Kepler half a century earlier. What he realized explained the motions of planets and the moon as well as falling objects on Earth. The answer, if he could find it, would also have to resolve the riddle of why all bodies fall at the same rate regardless of their mass. At first, Newton didn't name the force explicitly. He knew something had to attract the moon if it was to remain in orbit. The law of inertia stated that the moon would tend to travel in a straight line unless some force acted upon it. He coined the word centripetal force for any force which is directed inwards towards the center of an object's motion. Centrifugal force is the apparent force that appears to draw a body away from the center of rotation. Newton learned from Kepler. He also learned from Galileo. In his work on falling bodies, Galileo studied projectile motion. Newton realized that a satellite, like the moon, is a projectile. He considered projecting a stone horizontally from a high mountain. The graphic on the lower right is an illustration of this idea taken from his book. The animation shows it even better. If the stone is given a small initial velocity, it doesn't travel far horizontally before hitting the Earth. Now, if the stone is projected with a greater speed, it travels further before it hits the ground. The greater the initial speed of the projectile, the further it goes before it falls to the Earth. If the stone is given enough velocity, it will orbit the Earth. The stone is continually falling, but because of the curvature of the Earth, it never reaches the ground. Instead, it orbits. The moon, Newton realized, has just the right speed to orbit the Earth, always falling toward it but never reaching it. He realized that a satellite, given enough initial velocity, could orbit the Earth. In physics, an inverse square law states that a specified physical quantity, or intensity, is inversely proportional to the square of the distance from the source of that physical quantity. The animation on the left depicts a physical quantity that originates from a point and emanates out spherically. The diagram on the right depicts the same thing with cross-sections of the sphere. The amount of energy for a fixed area diminishes as the sphere grows. The total energy never diminishes, however. It's always conserved. Think of this like blowing up a balloon. As the balloon gets bigger, the rubber membrane gets thinner. Blow it up too much, and the balloon pops. Gravity works the same way except that it doesn't pop. It expands out spherically to infinity. This is how Newton's law of universal gravitation follows an inverse square law. The effects of electric, magnetic, light, sound, and radiation phenomena do the same. The surface area of a sphere is 4 pi r squared. The surface area is proportional to the square of the radius. As the emitted radiation gets further from the source, it's spread out over an area that is increasing in proportion to the square of the distance from the source. Hence, the intensity of gravity passing through a unit area is inversely proportional to the square of the distance from the point source. In the diagram on the right, the squares are a fixed area. At r, we're looking at 1 square area. The energy that passed through 1 square at r passes through 4 squares at 2r and 9 squares at 3r. If you measure the gravitational field in 1 square at 3r, it's 1/9 as strong as the field at r. Newton established that any force involved with orbital motion would have to diminish as the bodies move farther apart. Kepler's laws led him to understand that it would be inversely proportional to the square of the distance between them. Newton further theorized that the force of gravity was proportional to the mass of each of the two bodies. If m1 and m2 are two masses, and r is the distance between them, Newton theorized the force between them would be in the form of an equation like this. He had a problem. He wanted to relate the mass and distance to force, but the units didn't work out. To solve that, he invented a constant g that would later be called the universal gravitational constant. Don't confuse this with the lowercase g, which is the acceleration of a body on the surface of the Earth due to Earth's gravity. If we put the units into Newton's equation, we have F newtons, the measure of force, equals m1 kilograms times m2 kilograms over r meters squared. If we just express the units, we'd have that newtons equals something times kilograms squared over meters squared. To make the units work out, the unknown units have to be newtons times meters squared over kilograms squared. G then would be in these units, newtons times meters squared over kilograms squared. A newton is the force required to accelerate a kilogram of mass at the rate of 1 meter per second squared. Now we can express the units this way. A kilogram meter per second squared equals an unknown times a kilogram squared per meter squared. The units here would be meters cubed over kilograms second squared. G would equal some quantity of meters cubed over kilograms second squared. Newton expressed it as a hypothetical constant. It wasn't until much later that it was quantified by Henry Cavendish in his famous experiment. It's 6.693 times 10 to the minus 11th. That's as precise as we know it today. It's actually the least precise constant of all the constants that we have for the physical universe. Here's the gravitational constant in other units. Why are the units so strange? It's because of the way the fundamental units were defined. The gram was originally defined as the mass of 1 cubic centimeter of water at 4 degrees centigrade, making the kilogram equal to the mass of 1 liter of water. Newton discovered a fundamental relationship between mass and the force of gravity. Had he been able to redefine standard units, he would have equated mass with gravity. Then there would have been no need for a gravitational constant. For the equation F equals ma, he had this opportunity. Because he was defining force for the first time, he could simply state that a newton was equal to mass times acceleration squared, which results in units of kilograms per second squared, with no conversion constant. For the force of gravity, however, he was stuck with units of mass that were based on water. Even though Newton explained what he meant by mass, some people think that mass is a quantity which is defined by this equation. If you know the magnitude of the force acting on an object, measure the magnitude of the resulting acceleration. Then the mass of the object is m equals F over a. Other people think that the second law is a definition of force. Knowing the mass of an object, measure its acceleration, and the applied force can be found. If the second law is a definition of either mass or force, it's not a deep discovery in physics. It's simply a definition. If the equation is used to define two of the three quantities, then it has no meaning at all. The same held with the law of gravitation. It simply accounted for the force that kept the moon or any other satellite or planet in its orbit. It's not that F equals ma is simpler and the law of gravitation is complex. G is also not some mysterious constant that characterizes some aspect of the universe. It's necessary because we chose to define the kilogram as 1 liter of water. If the kilogram were defined in terms of gravity produced by mass, there would be no need for a constant. Force is a vector quantity. The relation above shows only magnitude. Since gravity tends to pull objects directly toward one another, the direction of the gravitational force between any two bodies is along the lines that join them. We signify the direction by using the unit vector r, pointing like this, in the direction from one mass m2 to the other, m1. The unit vector r has a magnitude of 1. The force on m2 being attractive is in the direction opposite to r. Therefore, the vector equation for the universal law of gravity is F equals minus g times m1 m2 over r squared times the unit vector r. This equation tells us that the force between 2 point masses, which are idealized objects, having all their mass centered at one point. Newton proved with his newly developed integral calculus that a perfectly spherical planet with uniform density can be considered mathematically as a point mass. In fact, this couldn't be proven without integral calculus. Considering masses as point masses greatly simplifies the math. Let's consider the forces the other way around. The force that m2 exerts on m1 is F21, and it points to the right. F21 equals minus g times m1 m2 over r21 squared times the unit vector r21. Newton's third law tells us that for every action there's an equal and opposite reaction. If m1 exerts a force F21 on m2, then m2 exerts an equal and opposite force F12 on m1. Let's add a third mass, m3. The force it exerts on M1 is minus g M1 M3 over R31 squared times the unit vector R31. The force F1 is a vector sum of the force on F21 and F31. That equals this. Using the superposition principle, the resulting force on a mass is the vector sum of the individual forces. It's an important aspect of Newton's second law, which allows us to calculate the gravitational force on an object from any number of bodies. Now let's talk about the law of conservation of energy, one of the most fundamental laws of physics. A conservative force is one where no energy is gained and none is lost. It's one where energy is always conserved. The notion of energy was not understood until the middle of the 19th century. There were inklings that predated Newton. The experiments that Galileo performed with balls rolling down inclined planes only gave hints. It wasn't until later that energy was better understood. We already talked about Galileo's law of falling bodies. We want to talk again about experiments he did with inclined planes. He did more, however. He found that once a ball had finished rolling down one inclined ramp, it would proceed to roll back up another to the same level. He never saw that exactly. He took great care to minimize friction, which is a non-conservative force. He had a notion of friction, and he surmised that in its absence, his rolling balls would oscillate back and forth forever. This animation is a demonstration of that. The first downward inclined ramp is at 60 degrees, the second is at 45. There's a horizontal plane in the middle. If there was no up ramp, Galileo concluded that the velocity of the ball on the horizontal plane would go on forever. This is the basis of his law of inertia. Once we have a law of inertia, we can see why the ball starts up the second inclined ramp. We don't have a good rationale for why it always reaches the same vertical height it started with, but we know that at the bottom it has an inertia that carries it up the upward ramp. Since the ball finds its origin, there's something conserved in the process. The name we give to the conserved quantity is energy. There are two types of energy. When the ball is placed at the starting position, we say it has potential energy. That's energy that the ball has by virtue of its position. If the ball is then released, it starts rolling. As it rolls down, it picks up speed. By the time it reaches the bottom, its potential energy is now gone. In the place of potential energy, the ball now has energy of motion. The potential energy has been transformed into another form of energy. We call the energy of motion kinetic energy. As the ball continues ascending the second inclined ramp, it slows down. It's losing kinetic energy, but in return, it's regaining potential energy. When the ball finally comes to rest at the top of the second up ramp, all of its kinetic energy is gone and has been transformed back into potential energy. Because the ball height is precisely what it was at the beginning, it has the same potential energy at the finish as it did at the start. Before the experiment was run, Galileo lifted the ball to the starting position. In doing that, he applied a force that opposed gravity. That's what gave the ball its initial potential energy. When he released the ball, the force of gravity caused it to accelerate down the ramp. At the bottom of the ramp, its inertia makes it roll horizontally and then back up the second ramp. If the ball slows down on the up ramp, it's because its inertia now opposes the force of gravity. We'll formalize these dynamics. To formalize this, we need to relate energy to forces. We do that with the concept of work. Work is an energy transfer of one form to another carried out by a force acting over time and distance. The simple case is a constant force of magnitude F that moves an object a distance h in line with that force. The work done, W, by the force is defined as the force F times the displacement h. If you lift an object of mass m in such a way that it is at rest after you lift it, then the lifting force is equal to the weight mg of the object. Mg is the force at the surface of the Earth, which, if we stay close to the surface, is constant. Since F, the force, equals mg, the work done to raise the object up to height h equals mgh. Here the work goes into potential energy. Let's call that U. Gravitational potential energy in the gravitational field at the surface of the Earth can be given in the simple form U equals mgh. This sets up the beginning of Galileo's experiment. The dimensions of work are force times distance. The SI unit of work is the joule, which, since it measures force times distance, is 1 Newton meter. Recall that newtons are kilogram meters per second squared. A joule is then kilograms meters squared per second squared. Watts expressed the rate of energy conversion or transfer with respect to time. It's the number of joules performed per second. That equates to Newton meters per second, which is equivalent to kilogram meters squared per second cubed. A joule then would be equal to a watt second. Other units are the foot-pound, which equals 1.3558 joules, and the erg, which is 10 to the minus 7th joules. 1 joule is 10 million ergs. Let's describe Galileo's experiment now with the formalism of potential energy equals mgh. In his experiment, Galileo first lifts the ball to a height h, performing work on it by applying a force to balance the force of gravity. Work is done by the force that Galileo applies and against the force of gravity. Here the work represents a transfer from the world outside the ball, namely Galileo, to the ball. Since the ball is displaced without accelerating further, all the work goes into potential energy. It's only stationary for an instant before gravity starts it down the ramp. Nonetheless, at its starting position, it's stationary. Next, Galileo releases the ball. Acting solely under the force of gravity, it rolls down the incline. During this stage, gravity is the force that performs work on the ball. Our theory is that energy is conserved here, all the way down the ramp and even at the bottom. The work going down the ramp represents a transfer from potential to kinetic energy. On the horizontal section, gravity has no effect. The horizontal ramp keeps the ball from falling further. It thus travels at a constant velocity to the beginning of the up ramp. The ball then rolls back up the up ramp and reaches its original height. Along the way, as the ball was going back up, there was a transfer of energy back from kinetic to potential energy. At its peak, it pauses and is momentarily stationary. Energy is conserved. If the potential at the start were mgh, and if the ball reaches the same height on the up ramp, then the potential energy at the finish is also mgh. How does potential energy arise? It occurs in fields of attractive or repulsive forces. Gravity is an attractive force. This is how we typically depict force lines. The density of the arrows represent the strength of the force. In this picture, it's not meant to be exact, just representative. This is one way of representing the 1 over r squared law. As you move away from the source of attraction, the field density diminishes. The field lines extend out to infinity. You'd measure a field with a test mass. It's better to use one that's significantly smaller than the field source. Otherwise, the test mass's gravitational force interacts with the central bodies. In mathematics, we use a hypothetical test mass. Another kind of a field is an electric field. If we change the central body from a mass to a positively charged particle, it sets up an electric field. And as a test mass, we'd use a negative particle. And another kind of a field is a magnetic field. When the ball reaches the bottom of Galileo's incline, where the height h equals 0, it will have lost all its potential energy, u. You might wonder why we say there's no more potential energy. After all, the ball still has potential. If this apparatus was on a tabletop, the ball could conceivably fall to the floor. If Galileo was in a 2-story building, the ball could have rolled down the stairs. In fact, the only place where the potential energy would be 0 would be at the center of mass of the Earth. We arbitrarily set the tabletop as our reference for 0 potential energy. It's arbitrary and could be set at any point. Once the ball gets down to that 0 point, the potential energy is converted into kinetic energy, K. Because energy is conserved, we now know exactly how large K will be at the bottom. It will be equal to U at the top. K, being the energy of motion, does not depend on where the ball is as U. The potential energy does. It depends on how fast the ball is moving. There's a connection between kinetic energy and motion. In this equation for K, however, we've expressed the kinetic energy in terms of position. While that gives us the right value, it doesn't express K as a measure of motion. For that, we need another derivation. Here we formalize kinetic energy. Let's assume that rather than traveling on an incline, the ball drops straight down. That's a simple case that leads to the right equation for kinetic energy. Here's the displacement vector r. Velocity v of t equals the acceleration times time. Here we're dealing with gravity, so the acceleration is constant and is g. We can express velocity more generally as v equals gt. The equation for position is 1/2 gt squared. We derive the formula for potential energy based on the position of the ball at its highest height, h. Rather than h being the highest point, let's make h be the height of the ball at any point in time. P of t then equals h. H is thus 1/2 gt squared. That's the same equation the other way around. g, the acceleration of gravity, is negative, and the displacement, h of the ball, from the top of the ramp to the bottom is also negative. 1/2 gt squared, where g is negative, results in h, which is also negative. If we multiply both sides of this equation by g, we get that gh equals 1/2 g squared t squared. If we multiply both sides by 2, we get 2gh equals g squared t squared. Let's combine gt squared into one term. As we said earlier, velocity is acceleration g times time. We can make that substitution in the previous equation. If we multiply both sides of this equation by 1/2 m, we get mgh equals 1/2 mv squared. We said the kinetic energy K equals the potential energy U, which equals mgh. Mass times gravity times height characterizes an object at rest. 1/2 mv squared characterizes an object in motion. It equates energy to velocity. The kinetic energy is 1/2 times the mass times the velocity squared. We define work as force times displacement. Near the surface of the Earth, the gravitational force equals mass times g. Work and potential energy thus equals mgh. We introduced Newton's universal law of gravitation, which states force equals minus g times m1 m2 over r squared. G equals 6.693 times 10 to the minus 11th. If we assume m2 is much smaller than m1, F equals ma. m2a equals gm1 m2 over r squared. The m2's canceled, and we're left with an equation for acceleration. The mean radius of the Earth is 6.383 times 10 to the 6th meters. I adjusted this number to make the acceleration come out. The mass of the Earth is 5.95 times 10 to the 24th kilograms. If we plug in those numbers, we get 9.81 meters per second squared for acceleration. That's the result that Galileo determined. If we're 250 meters above the surface of the Earth, the acceleration goes down by about 0.001 meters per second squared. Not enough to notice unless you're measuring very precisely. Go up to 1,000 kilometers above the surface, however, and the acceleration drops appreciably to 7.33 meters per second squared. In the denominator of this equation, we have the radius of the Earth plus 1.0 times 10 to the 6th. 1.0 times 10 to the 6 meters is 1,000 kilometers. To account for altitude, or distance from the center of the Earth, we express potential energy this way. Recall that we set an arbitrary 0 point for potential energy. If we consider the Earth as a point mass, the potential energy point could be the center of mass, but the convention is to do just the opposite. The 0 point for potential energy is far, far away from the center of mass. Specifically, it's at infinity. That means the potential energy in a gravitational field will be a negative number. If the reference point were at the center of mass, the formula for potential energy would yield a very large number. Since we're interested in comparing potential energies at different locations, smaller negative numbers are easier to deal with. Since our reference point is no longer at the surface of the Earth, we'll use r rather than h. Potential energy is mr times minus g times the mass of the Earth over r squared. There's an r in the numerator and an r squared in the denominator. We can take out the r on top and one of them on the bottom. Potential energy is thus minus g times m times the mass of the Earth over the distance from the center of the mass. Kinetic energy is always 1/2 mv squared. At infinity, potential energy would be 0. So would kinetic energy. Based on this, we can compute the amount of energy required to send an object to infinity. It's u at infinity plus k at infinity, and given how we chose our 0 potential energy point, the total energy equals 0. Let's say we had an object on the surface of the Earth and we wanted to send it out to infinity. How much energy would that take? Since energy must be conserved, potential energy at the surface of the Earth plus kinetic energy at the surface of the Earth must equal the total energy at infinity, which is 0. Here is the potential energy and kinetic energy at the surface of the Earth based on the equations we just derived. We can move kinetic energy to one side, which leaves potential energy on the other side. There's an m on both sides that cancel, and because we want to solve for velocity, we'll multiply both sides by 2. V squared equals 2gm Earth over r Earth. V thus equals the square root of that. Here we plug in values for g, and the mass of the Earth, and the radius of the Earth. That equals 11.19 kilometers per second. If you launch an object at that speed at the surface of the Earth, it will travel to infinity. We call this escape velocity. Here's an animation where we don't quite reach escape velocity. The initial velocity is less than 11.19 kilometers per second. The graph on the bottom is the acceleration. Notice how it declines at the apex and then increases when the ball reaches the ground. This is because gravity diminishes with the distance from the center of the mass of the Earth. Here the ball reaches escape velocity. The scale on the left is much larger than the previous slide. The plot in the middle is acceleration. The one on the bottom is velocity. Notice how rapidly the acceleration drops off. As the ball gets farther and farther away from Earth, the acceleration goes quickly to zero. Notice how the velocity changes too. The ball is never coming back to Earth. That's what escape velocity implies. The velocity, however, gets slower and slower. If I could show you the ball at infinity, you'd see it come to rest and never fall back. If the ball travels from the surface of the Earth at a faster velocity than the 11.19 kilometers per second escape velocity, it would keep going, and as Buzz Lightyear would say, to infinity and beyond. This gives you some sense of the kinematics of objects traveling away from a gravitational field. A common analogy is a gravity well, which we'll talk about later. It uses a constant downward gravity and object moving horizontally to explain three-dimensional gravity that diminishes over distance. Here we've taken into account the escape velocity of the Earth. The Earth orbits around the Sun, however. A ball starting at the Earth would need to be going 42.18 kilometers per second to escape the gravitational force of the Sun. If we look to the galaxy, the ball has to escape the gravitational force of the Milky Way. For that, it requires speeds between 500 and 600 kilometers per second. You can see why in our local galaxy there's no real inertial frame of reference. The same holds for the entire universe. The proper motion of a planet or satellite in orbit around a central body has a velocity that is slower at apoapsis and faster at periapsis. Since there is no net force acting on the orbiting body outside of the gravitational force from the central body, the energy of the orbiting body must be conserved. U plus k must equal a constant. In the case of potential energy, U equals minus gmm over r, where little m is the mass of the satellite and big M is the mass of the central body. We're assuming here that big M is much larger than little m. As the distance from the central body increases, like at apoapsis, the potential energy increases. As r gets larger, 1 over r gets smaller. Since u here is a negative number, a smaller value represents an increase in potential energy. Likewise, as the distance from the central body decreases, like at periapsis, the potential energy decreases. The kinetic energy must increase to compensate. Thus, the satellite must move faster. In the animation, as the satellite gets nearer the Earth, the velocity has to increase to account for the loss of potential energy. The kinetic energy increases with the velocity squared. Looked at the other way, the velocity squared increases so that it accounts for the loss of potential energy. Forces act on objects with respect to their center of mass. It's one of the discoveries that calculus uncovered. For a symmetrical spherical mass, the center of mass is at the geometric center. Hence, a force acting on the mass acts as if all the mass were concentrated at the center. That assumes a constant force. The force of gravity varies depending on the distance from the source. We've said before that if it's a small object near the surface of the Earth, the force is the mass times g. The gravitational force, however, is minus g m1 m2 over r squared. If the object is very large, the force acting on the side nearest the source of gravity will be larger than the force acting on the far side. The center of gravity will shift towards the source of gravity. When we looked at orbiting bodies, we talked about one orbiting the other. This works somewhat for small planets or satellites orbiting around very large masses. Orbiting bodies, however, don't work that way. Rather than one orbiting around the other, the two co-orbit around their common center of mass. This is what you see in the animation. The equal and opposite forces of gravity are focused on the center of mass. The common center of mass between Jupiter and the Sun is at the edge of the photosphere of the Sun. Remember that Jupiter is 317 times more massive than the Earth. The Sun is 333,000 times more massive than the Earth. That means that the Sun is only 1,050 times more massive than Jupiter. That's enough to place the center of mass between the two far from the center of the Sun. Since the two bodies co-orbit each other, they both are following somewhat elliptical paths. The Sun's is smaller, but nonetheless is noticeable. This animation shows the effects of the planetary objects on the Sun. Jupiter and Saturn, being the most massive planets, have the greatest effect. Neptune also has a noticeable effect, but since it's so far away, it takes 164 years to complete one orbit. Jupiter only takes about 12 years. Saturn is about 30. Ever wonder how astronomers find distant planets? They can't see them against black space. If the planet crosses between us and the stars, which astronomers call a transit, it's conceivable that a planet could be seen, but you need a very powerful telescope. One technique that is widely used is to measure the wobble of stars. If a planet like Jupiter is orbiting a star like our Sun, we would see a noticeable shift. Galileo proved that objects fall at the same rate no matter what their mass. Newton later showed that the force of gravity equaled minus g times the mass of the object times the mass of the Earth over r squared. Since force equals mass times acceleration, we can express the forces with this equation. The mass of the object is on both sides of the equation and thus cancel. The acceleration of gravity is constant no matter what the mass. If you had two bodies whose mass equaled the mass of the Earth, they would attract each other and would meet at their common center of mass. Here the force equals minus gm1m2 over r. The force exerted by mass 1 on mass 2 is minus g times m1m2 over r squared. The force exerted by mass 2 on mass 1 is positive g times m1m2 over r squared. The forces cancel out. That's why the center of mass doesn't move. The acceleration that mass m1 experiences, a1, is minus gm2 over r squared. Likewise, the acceleration that mass 2 experiences, gm1 over r squared. It appears that all of this is consistent with Galileo's discoveries. If mass m1 is substantially smaller than the mass of the Earth, the center of mass will be at the red dot. They will both fall to a common center of mass. If mass m1 were a tennis ball, you would not see that much Earth displacement. However, even a tennis ball will displace the Earth somewhat if it falls downward. With Newton's law of gravitation, we can derive Kepler's laws. We can also derive orbital motions that weren't recognized by Kepler. Let's start by characterizing the gravitational force between three objects in line with each other. Recall that Newton's theory of gravitational force is a force that acts between two massive bodies. Assume they are a distance r apart. This is the unit vector r for the force. It's the line between one body and the other. The force that object 1 exerts on object 2 is depicted by this vector here. Newton's law of gravitation says that the force is g times m1m2 over r squared. The force exerted by mass 1 on mass 2 is minus gm1m2 over r squared times the unit vector r12. The negative sign is a convention. If the force were propelling mass 2 to the right, it would be positive. Let's apply this to our three objects. Here's the distance between mass 1 and 2. Here's the distance between 2 and 3. And here's the distance between 1 and 3. Here are the vectors between 1 and 2. Here's the force that mass 1 exerts on mass 2. Likewise, here's the force that mass 2 exerts on mass 1. Newton's third law states that F21 must be equal and opposite to F12. Here are the forces between mass 2 and 3. And here are the forces between mass 1 and 3. Like we said before, this is the equation for the force that mass 1 exerts on mass 2. If you know the masses of the objects and the distance between them, this is a simple calculation. Here's the equation for F21, here's the equation for F32, and here's the equation for force F23. There would be similar equations for F31 and F13. The total force acting on mass 1 is F21 plus F31. F21 and F31 are both vectors, meaning they imply a magnitude and direction. That results in a net force on vector F1. Here's the force that acts on F2, and here's the force that acts on F3. If we know the forces, we can derive the acceleration. F equals ma. That results from Newton's second law. A, the acceleration, thus equals the force divided by the mass. With this equation, we can determine the displacement for a given time interval. It requires that we know the initial position p, the initial velocity v, and the force imposed imposed by the acceleration which we plug into this equation. Kepler's methods don't work for these kind of dynamics. Newton's force equations are much simpler and allow us to account for more than two bodies where none of them has a mass that dominates. Here we show some animations to demonstrate that concept. These are equal masses. The dark blue is the same distance from the light blue as the light blue is from the yellow. If we set these objects in motion, the gravitational force brings them together. The light blue is at the center of mass of the system. The blue and yellow drift simultaneously into the light blue. The net force on the blue mass was due to the light blue and the yellow masses. The light blue exerts more force since it's closer, even though the yellow has the same mass. It's further away. Remember that the gravitational force diminishes with 1 over r squared. The light blue feels a force from dark blue and yellow, but since they are equidistant, and since they remain equidistant, the light blue mass doesn't move. If we change the distances, we can see that the center of mass shifts. It's the small red dot. All three objects are the same mass here. The light blue and yellow are closer to each other. They collide first. Their combined masses then meet the dark blue at the red center of mass. Here the light blue does not stay stationary. Since yellow is closer, it exerts greater force and causes it to move to the right. Dark blue exerts a force on light blue, but since it's farther away than yellow, it doesn't contribute as much to the motion. If we took dark blue out of the animation, the light blue object would travel to the right faster. When light blue and yellow combine, their mass doubles. It moves slowly to the left. Dark blue moves quicker to the right. The combined light blue and yellow exert twice the force on dark blue as dark blue exerts on the combined masses. Now we change the masses. Dark blue is more massive. Notice that the red center of mass is shifted to the left. Light blue and yellow still collide first. All three meet at the center of mass. Now we want to look at an animation where the objects are not aligned in a straight line. The force vectors for three objects would look like this. To determine the total force acting on mass 1, we'd add vectors F21 and F31. That results in a vector F1 that points in this direction. We do the same for the other forces. Now we don't just get a different magnitude of force, we get a change in direction. The net force is the sum of all the forces. That holds for three bodies, 4, 5, or as many as you want. We call this the n-body problem. Here the three equal masses are equidistant from each other. They form an equilateral triangle. Notice the red center of mass right in between them. They all three simultaneously meet at the center of mass. Here we've increased the mass of one of the objects. Notice how the center of mass is shifted. All three now converge simultaneously on the center of mass. Now let's look at orbital motion. Here we have a sun and a planet. The red vector is velocity. If we didn't have that, the planet would fall right into the sun. The purple vector is the gravitational acceleration. The sun doesn't have an initial velocity, but according to Newton's third law, the planet exerts an equal and opposite force on the sun. In this case, we get a nice circular motion. The sun doesn't appear to move much. Its mass overwhelms the planet. Here we reduce the initial velocity of the planet. Notice how the velocity vector and the acceleration vector changes. As the planet gets closer, the acceleration increases. So does the velocity. The increased velocity is enough to keep the planet from colliding with the sun. It whips the planet out to the apoapsis point. The gravitational pull of the sun slows the planet down until it comes around. At apoapsis, it starts going away from the sun and starts on its trajectory to the periapsis point. None of this was done with Kepler's equations. This was all done with Newton's force equations. This was a key discovery for Newton. He found that with his force equations, he could derive Kepler's laws that said that planets orbit along ellipses and that they sweep out equal areas in equal time. I've actually said this backwards. Newton's discovery that the gravitational force diminishes by 1 over r squared was a result of Kepler's discoveries. Equal areas swept out in equal time only works if the force comes from a central body and the shape is an ellipse only if the force diminishes by 1 over r squared. The ellipse led Newton to discover the 1 over r squared relationship. This is a similar animation. This time we sped up the initial velocity. We had to zoom out in order to show this. The periapsis point is switched with the apoapsis point. Let's consider the case where two bodies of equal masses have an initial velocity. There is no longer a central body. These two objects are co-orbiting each other. Per Newton's third law, the force applied by red to yellow is equal and opposite to the force applied by yellow to red. While the path of these orbits look elliptical, they're not. Elliptical orbits only occur when there's a very massive central body and a very small orbiting body, like the Earth and an 8,000-pound satellite or the Sun and a very small Earth. While Kepler's laws helped Newton derive his force equations, Newton showed that they do not apply in all cases. This is a case in point. Each of these objects orbits around their common center of mass. None of them follows an ellipse. If we change the force equation so that the force is proportional to 1 over r, here's what the motion would look like. Things don't move like this in our universe. Here the force is constant. This is what Galileo thought. Things in the universe definitely don't move like this. This confirms the 1 over r squared relationship. Here's a case where the red object is more massive. They both appear to be following elliptical paths, but they're not. The red follows a little oval shape. The yellow follows a larger oval shape. This is how two bodies move in the real world. Our Earth doesn't orbit the Sun. The Earth and Sun co-orbit each other. Let's now introduce another object. These all have equal masses. Their initial velocities are different. Notice the center of mass. It's moving. Here the forces are all between the three objects. There's no external force. While there's relative motion, you'll notice that the center of mass moves in a straight line. That's because it has no external force acting upon it. Even with some pretty quirky motion, the red center of mass still moves in a straight line with a constant velocity. You can definitely see here that nothing is moving along the path of an ellipse. Kepler's laws were only good approximations of the motions of the planets. Here's a three-body example. And watch what happens to the light blue. The orbit actually changed direction. Notice how light blue flattens out to yellow. This is common in orbital dynamics, and this is why galaxies tend to flatten out into planes. Here we have several objects. We set up initial velocities randomly. And even here, the center of mass would be moving in a straight line at a constant velocity. Here's another example. These are very complex motions simulated with very simple force equations. And when you see things disappearing, that's because masses are colliding. In these animations, there's an interesting phenomenon. If you let the objects get too close, 1 over r squared starts to approach infinity, and you can get very fast velocities. So much so that you can exceed the speed of light, and you can get more potential energy than you started with, which is a physical impossibility. Newton's force equations allow for eccentric motion, kinds of motion that I just showed you. They go beyond Kepler's ellipses. I also derived for you the formula for escape velocity. What if the yellow mass travels at a velocity that is at or exceeds the escape velocity? It follows this parabolic pattern. Newton figured out that a body that orbits a very massive central body will follow the path of one of the conic sections. We've already talked about circular and elliptical orbits. We can characterize an ellipse as the intersection of a cone with a plane. This is what is meant by a conic section or a conic. If the cutting plane is level, you get a circle. That's an ellipse with eccentricity equal to 0. If the cutting plane is tilted, you get an ellipse. An ellipse has eccentricity between 0 and 1. If you keep tilting the cutting plane, you get a parabola. A parabola is an open curve, meaning that the legs of the U-shaped figure go out to infinity. A parabola has an eccentricity equal to 1. When the cutting plane is vertical, you get a hyperbola. Its eccentricity is greater than 1. These are the three conic sections: ellipse, which includes circles, parabola, and hyperbola. This animation shows the shape going from a circle to an ellipse to a parabola and then to a hyperbola. So there's the circle, there's an ellipse, there's the parabola, and there's a hyperbola. A parabolic or hyperbolic trajectory is an escape trajectory. It's not a bound orbit like a circle or an ellipse. This is an animation of what might have happened to Apollo 13. It was thought that if Apollo 13 had not re-entered the Earth's atmosphere, it would skip off and remain in a highly elliptical orbit around the Earth for years. Based on Newton's equations, however, it was later determined that something different would happen. Now watch what happens when the capsule approaches the gravitational force of the moon. It shifts the orbit. And instead of orbiting the Earth, the capsule's on a collision course. So the astronauts would not have survived, but they would have returned home eventually. There are various trajectories that are used to propel objects like probes into the outer parts of the solar system, and they are either parabolic or hyperbolic trajectories.